When studying simple energy, one system that's very common is a spring-mounted mass. And we've already seen in the lab that it's possible to study conservation of energy while ignoring the gravitational effects of the system. So if we had a basic mass hung from a spring, and we extended that string by if we extended that spring by applying a force such that we displace the mass an extra distance x. Let's assume that this would be the maximum displacement, and therefore x would equal negative a, or positive a if we were doing it in the opposite direction. It's fairly irrelevant in this case, as long as a is our distance. Then when we hold it here, we can say that it has stored elastic potential energy. However, once we let go, because of that stored elastic energy, we expect the spring to apply a force back up in the vertical direction, causing a motion here that would be the maximum value at the equilibrium line where the mass started. We know that the mass would move with its momentum past this point until it got up here, where the spring constant would squish back down, store potential energy, and then push it back in the opposite direction. But what I'm most interested in is just this first transition of energy from here to here. If I say that this is my initial condition and this is my final condition, then we end with a kinetic energy that we would call prime as our after condition. So looking at the conservation of energy in this way, we have E equal E prime as PE equal to KE. And then, of course, based on the formula, we can substitute these two things. Let's go ahead and just take this over here for room's sake. If I say 1/2 kx squared equals 1/2 mv squared. But of course, at these conditions, from here to there, we know that the x is the maximum value, which is a, negative a, but we're going to square it, so that's okay. And the half term is common, so that drops out. And then, of course, at this point, v is v max. And so what we see is that k times a squared is equal to m times v max squared. We're going to hold on to that for just one moment, but if it's useful at this time to rearrange this to put some terms in terms of the physicality and the motion on either side. So we're going to divide by v squared and leave this as a squared over v max squared equal to m over k. So these are the motion characteristics and the physical characteristics isolated on either side. And of course, squared. And of course, a over v max then is just the square root of m over k. And I've done that for a purpose, and I want to show you what that purpose is. Something that's very interesting that we're not going to get into at this point, but we are going to see later, is that natural oscillation in this way is described as simple harmonic motion, SHM, simple harmonic motion. Simple harmonic motion is interesting because it's periodic repetitive motion that repeats over time for an indefinite period of time. And we've already seen a couple cases of this, the spring bouncing, but also going in a circle. And so you can imagine that if we were tracing out a circle, in this case, an object spinning in this way, rotating around a particular circumference in a period of time consistently over and over and over again, we know that the velocity can be described as 2 pi r over t. Of course, since it would be a uniform rotation, r is maximized, and so we're going to go ahead and let r equal the amplitude, and then we're also going to recognize that the velocity is the constant speed around the circle, and so for the same reasons, v is equal to v max. We're going to look at a derivation where it's much more obvious that these are true, but for now let's just take that on faith based on what I've described. Given that characteristic then, we know that based on this formula, v as v max would be equal to 2 pi times a divided by t. So, in combining and solving, we can solve this for t, and we end up with a period that is equal to 2 pi times a divided by v max. And if we go ahead and separate this as 2 pi times the quantity a divided by v max, we notice that the period is a function of these motion characteristics. But we can also say that simple harmonic oscillators, things oscillating in simple harmonic motion, share characteristics that can be described similarly. So we can take this term from a completely different system, right, springs and masses, and utilize it here in the circular motion. And so what we end up with is a period equal to 2 pi times the square root of m over k. And what we see is that the period can be described for a circular motion object as being mass divided by spring constant. Now, of course, there are no springs, so this period has no true meaning for this system. And of course, the period of a rotating system is a fairly easy idea. However, if we go back to the top and think about this natural oscillation, the time it takes for this to oscillate up past its equilibrium position, back up to the highest point, back down to the middle, and then back down to where this mass would be, that would be one complete oscillation, right? One wave, as it were. And so that's valuable in the sense that the period, we now recognize, can be calculated as a function of the physical characteristics of mass and spring constant, right? And so this formula can be utilized in that formula, and as association can be utilized in any formula where we know the physical characteristics describing the oscillatory motion. So this can also be transferred in certain terms to waves. And we're going to look at that a little bit deeper when we do some more exploration in sound and light. However, it's also very valuable to notice that period does not depend on amplitude. So what we find is that if we go back to this system, if I were to take this spring and stretch it out such that A was even further, right, much further down here, there's no reason that the oscillatory time for the wave, for the repetitive pattern, would change. And that has to do with the fact that as I stretch out the spring, it applies more force. The acceleration is greater the further down I go, which causes it to cover this distance back up to the equilibrium position in exactly the same time, regardless of how far the spring is stretched out. This is a very valuable formula moving forward for describing the period of these systems. And it was calculated through a relationship to something that wasn't necessarily driven by a spring, but yet applies.